In this video, I'm going to go over the answers that I came up with for homework 3 and homework 4. There's multiple ways, as I always say, there's multiple ways to actually get the right answer, but this is what I've come up with. All right, so the first problem is asking to create a function that generates a two-column array. Now, the trick here is that we can have two types of arguments. Two types of sets of arguments. The first way would be to just have a single argument, which is just a range that tells us what x needs to be. And then the second type of argument would be to have three of them, start, stop, and step, which are also the same as the arguments that go into range. So one of the ways to do this is to have three arguments, which is the maximum number that we can have, but then for two of them give default values, and in this case we just use the null value for Python, which is none. Now if either of these two variables are none, then we assume that the first argument is an actual range, but if they're not null, then we assume that then we want to use the second way of specifying these arguments, start, stop, and step. So then we use the first argument here and step to create this our object. So this object will essentially tell us what the values of x are. So we get the length of this r, then we create the output array, and we set the first column to cosine, the second column to sine, and we get the answer. So let's test it out. Let's import the modules, run the function, and run our tests. And you see here that we're either providing a range object or three arguments, and no errors, so it means it worked. Now the second problem is asking for a function that returns a to the power of b minus c, and then we need to iterate over the sequence 0 to 1, get 1,000 values for all three parameters. And we're going to write the first solution as a loop-based function, which is the naive version. So for this, essentially, we need 1,000 values. We keep that dynamic, so we're iterating over the range all the way from 0 to the length of a. Now, this implicitly assumes that a, b, and c have the same lengths. So normally we would write a check to see if that is true, otherwise we will get an error. But we initialize the output array, or list actually in this case, and then each time we iterate through, we append the value of a to the b minus c. So let's run this, and then we initialize a, b, and c here, and let's run our assertion, and it's, again, didn't give an error. So all good. Now the second solution was the NumPy based solution. Here's where it's very simple. As we've said during lectures, NumPy allows us to use scalar math operations directly, and NumPy will know what to do. So if a, b, and c are arrays, as in this case, we don't have to do all this boilerplate for loop, but we can just use this expression here, a to the power of b minus c. I know some of you use the NumPy power function or the NumPy subtract function. That's fine, but again, you can do the same thing closer, I guess, to the actual math notation here. So if we run this, and then we go again, no assertion error, so we're good. Now, we could, let's run some of the timing. So let's go back to rerun this naive solution, and let's time the, let's see, A, B, C. We get 395 milliseconds. Now let's run this function, overwrite the previous definition of f. Let's run this again. You see 0.6 milliseconds. So, and again, we've seen this before with the NumPy solutions. The second part of the problem is asking us to use broadcasting to generate a 24 by 12 by 6 array that's called samples. And each one of those will contain, each element will contain the value of f. Now, for the rows, we need to provide the parameter a, which is going to give us, well, it's from 0 to 1, but divided by in 24 increments. Same thing with B, we have 12 increments. Same thing with C, we have six increments. Now, because these are one-dimensional, if we try to run this with just A, B, and C, we're going to get an error. Because again, they're different lengths, and that's something that we probably should have checked before. But this is where broadcasting comes in handy. So what we need to do is we need to essentially create these fake axes or virtual axes in the places where they're missing it. So we know that for the rows we need that 24. So we're going to utilize A by adding these two axes here by using the new axis notation. So you see this A now becomes a 3D array. Without new memory though, we're just telling Python that, treat this as a 3D array. So it would be a 24 by 1 by 1. Now B would become 1 by 12 by 1, and C would be a 1 by 1 by 6. So now, because again, remember, the trailing dimension needs either to be 1 or match. So in this case, we always have 1, 1, 6. So it can work that way. So broadcasting works. So if we run this, so we didn't get an error. And then if we open a new one, cell, and we say sample shape, you see that it is, in fact, 24 by 12 by 6. So if we run, let's say 0, 0, 0, you see we get 1. And if we look at, let's say, samples 0, 0, 0, there we go, 1. All right, let's run another session, and everything works. Now, again, the only trick, I guess, here is just realizing how broadcasting rules work in Python, and the fact that we can essentially replicate the missing axes by using this keyword here. All right, and the last one, which I understand was a little bit confusing. I just wanted to make it, realistic. So we integrate over the volume. So apologies if I scared you off with the triple integral, but this essentially, we were asked to just calculate the mean. So we already have the samples here. Again, we go from 0 to 1, 0 to 1, 0 to 1. The derivative here, we just use 24 12 by 6, so we probably want to use something even larger in a real situation, obviously, because we want to better approximate the derivative. But even here, we can run the sample mean and then compare against the theoretical result, which is log 2 minus half, and you see that it's not that bad. If we change this, for example, let's say that we make 240, 120, and 60. This works again. So now let's compare. You see how closer we are now. So, pretty straightforward calculus. So, all right, that's homework 3. So let's move on to homework 4. And I'm just going to do both of them in a single video. So let's go here. Homework 4. All right, so let's import our modules. So the first question was about using the midpoint rule to approximate, again, an integral. And if we're approximating this, we have h, which again is a small increment, and we have the sum of the function of a minus half of h plus ih, and again I goes from I to n, from 1 to n. Now h is the step. We, depending on how many steps we want, and again the larger the steps, the more accurate we will be. We have b minus a over n. So let's write a function by just using a naive implementation using a for loop. So with this, again, we calculate the step. So we have HB minus A divided by N. Then we create an empty list and we loop through and we start, because again, the sum goes from 1 to N, we start from 1, because if we put range N, we will start from 0. So then we would just have to put I plus 1 here. So it depends on how you want to do this, but I prefer to just be as close to the notation as possible. So I just loop through 1 to all the way to N, excluding N plus 1, append the values here, and then calculate H times sum of S. Now there's another way we could do this. We could, for example, let's run this, it works. Well, let's run B here, but another way we could do this, we could say 0, and then we could, because we don't really need the entire list, right? So what we can do is we can just sum these values and then do this. Again, it works. So the only thing we did here, because we didn't need to keep the entire list in memory, so an alternative way is to just initialize the value of the sum with 0, just keep adding to it, so accumulate all the values to it, and then instead of just calculating the sum afterwards, do H times S. For an N that's very large, this is probably going to be more efficient, because again, we're not creating the memory for the entire list. All right, the second part is we need to write a vectorized midpoint function, and for that we just use the numpy sum function. So the way we can do this is we can use the f function, and we can call a minus 0.5 times h, which is the step at which we calculate, and then we vectorize this essentially by using the range of from n to n plus 1, which is the I here, times h, and then we use the numpy sum. Okay, so let's try this here. So, and I think I had a typo, so hopefully you caught that. The assertion works. And in the assertion, again, the way we call the function is that we pass an anonymous function here, which in this case is x squared minus 2 times x. So this is the function, but because we wrote the function this way, we are very flexible in terms of what that function will look like. All right, so now let's time these functions here, and let's do, okay, well, I think we asked for 1,000, so let's do that instead. Okay, the first one, you can see it's 446 microseconds. The NumPy solution is 31 microseconds. And remember that this one is not even keeping the entire list in memory, so the naive version would have been even slower. All right, so let's stay with the theme of naive implementations. So we're going to use non-vectorized function to recreate matrix multiplication. Now, one thing that we're also being asked is to just check to see if we have the wrong dimensions. So let's say we get two-dimensional arrays, A and B. We retrieve the shape, which is the size, so we have the number of rows, the number of columns, same thing for B. So now what we need to do is we need to make sure that A, C, and BR match. So the columns, the size of the columns of A matches the number of the rows in B. So if they do not match, then we just print this wrong dimensions and we don't do anything. We don't return anything. You see the return is within this else branch of the conditional. Otherwise, what we do, again, naive implementation, we create a new array, which is going to be ARBC in terms of dimensions, and then we loop through the rows of A and the columns of B, and then we go over the columns or the rows, the columns of A or rows of B to get the sum. And when we're done with this, we should have an array, and it works. So again, here we're using the numpy function of dot, and then getting the sum, because this will check against the naive multiplication of the two matrices, and then we get the sum. So we just want to compare the floating precision values here. There's another function of NumPy called matmult, which again also does similar thing, matrix multiplication. All right, so what I was looking for in the vectorized version, and I guess I should have been more explicit, is do not use the already ready-made NumPy function. However, as I was not explicit, apart from just talking about an efficient implementation, I accepted those solutions as well. But what I was looking for is essentially the same function, but in terms of the sum, we're essentially getting rid of that inner loop here. So we're using the NumPy vectorized sum to get this to get the sum of the product of A and B, the appropriate A and B's. So let's see, everything works. Again, in a real situation, you are all right that you would use this or matmult, but what I was looking for here is just replacing and getting rid of that inner loop, which should speed up the computation. All right, as always, any questions, anything about the homeworks, please do email me or post a question on the forum.